So let's look at our three-dimensional model again, right? So here I have my cyclohexane with my methyl group on it, and here it's all flat. I want to put this into the chair configuration, so I twist one carbon down and out of the plane and one carbon up and out of the plane. Okay? If you look, right, all of those hydrogens are staggered now, and the methyl group is staggered. Okay? If I have, in this configuration, I have the methyl group pointing up with these two axial hydrogens, they're going to repel each other. That's due to steric hindrance. So if I take and I bend this into the other configuration, that is I bend this one down, right, and I bend this one up, now you can see now my methyl group is in the equatorial position. It's pointing out and away from the cyclohexane, and I have not as much steric hindrance from the three hydrogens, which are much smaller. So the larger volume of the substituent, the more steric hindrance that I have, and the more likely it is to want to be out of the plane. So let's look at when we're going in our ring system, when we're going from one chair configuration to the other chair configuration. Remember, we talked about we're going to grab one carbon and pull it up, and the other one and pull it down. So while we're doing this, think about we're moving from one place to another. Right? There is some energy cost in going from one to the next. Okay? So when I'm turning this, at some point I go where this carbon is partway in between, right, to where we get to it's pointing up, but the other one is still pointing up. This is my boat configuration. Both of those hydrogens are pointing up. They're going to have these two axial hydrogens, remember, they're going to repel each other, so one of them is going to want to twist down and away, and we'll get back to our other chair configuration. This caused me some energy. There's also another configuration that's in between of these two, where it's halfway between a boat and a chair. We call this a twist boat, where we're in the process of twisting. Okay. So the lowest energy conformation is going to be my chair. The boat conformation is going to be a higher energy conformation than the chair, but it's not going to be as high as the twist as what it costs me to get from one or the other. Why is it that it costs so much? Well, if you think about this twist boat, this carbon is directly in between these, so I have all that torsional strain and steric strain from them repelling each other. Right? So the higher energy configuration is going to be in between the twist and the boat. The boat's higher than the chair, but not as high as the twist boat, right? And then back to this chair. So if this bond keeps repeating, then I'm going through this cycle of energy. All right, so if we have one substituent on here, right, we have our methyl group and the hydrogen that it shares its carbon with, right? We have this energy configuration is going to be a little bit higher. Well, let's draw that in another color. This one will be higher than our other chair configuration over here, but it doesn't affect our chair or our boat as much, right? But this chair, remember, is going to be a little bit higher in energy than the one where I have the methyl group out equatorial to the plane. We have one substituent on here. What if we want to put two substituents on here? All right. Now we have to think about they're repelling each other. And remember, it's not necessarily the size of an individual atom, it's the volume of a molecule. So if I have two methyl groups on here, let's put this one is axial up, and this one is going to be equatorial. There's no way for me to bend this chair such that I don't have one methyl group axial at all times. They're trans to each other. They're on opposite sides. If I take and I twist this one down to make this carbon equatorial up, then this one would be twisted to be axial. And we would wind up, both configurations would be the same. If I change it instead to where I have both methyl groups on the same side, now here they're both axial, that's going to be twice as much energy, right? And again, we're going to want to be in this configuration. Now, drawing this can be a little tricky. Think about if I've turned and I've tilted this one and turned it down, right? This is carbon number 1, okay? Which carbon is this carbon over here? It's this one back here. The methyl group is still going to be up, but it's equatorial. That can be a little tricky to draw. Think about our model. When we took and we tilted and we twisted that one carbon, we're changing the orientation and the relationship between all the other molecules, all the other hydrogen atoms that are on here. So all the rest of the molecule is affected when we take and we turn that one down, right? So when you have these two substituents, they're both up, right? They're cis to each other. They're going to be on one side of the molecule. When we turn one, we're going to be turning the other. Okay? Last piece. When we have two substituents of different energies, does it make a difference which one is axial up and which one is axial down? Well, so here, they both were the same, and they're both on the same side, right? So this makes a big difference. Over here, they were both equatorial. So this one's going to be much lower energy. But let's say I had a different substituent group. Let's change one of those methyl groups for chlorine. Over here, I have the methyl group equatorial and the chlorine equatorial. All right? So here I have the methyl group is equatorial and the chlorine is axial. All right? If I take and I turn that around, I bend this configuration up. Here the chlorine is equatorial and my methyl group is axial. Which one of these is going to be the lower energy configuration? If you think about it, chlorine has a mass of 35. My carbon, my methyl group, has a mass of 12 for the carbon plus 3 for the hydrogens. Okay? Remember, though, that this is important, that carbon, those hydrogens are on there, and there's some distance between them. So even though the chlorine has a higher mass, the methyl group has a much higher volume. Think about those hydrogens. There's a 1.8 angstrom bond to get to the hydrogen, and those hydrogens are out there in free rotation. I like to think about it like broccoli. They're kind of spinning around in space and making up a volume. Okay, so which one of those is going to be higher in energy? Is it going to be higher energy to have the methyl group axial or the chlorine axial? It turns out it's going to be higher for the methyl group. Why? Because remember, we're not just taking into account the size, we have to take into account the volume. And this has to do with our steric strain. Our methyl group, it looks like broccoli, okay? It's sterically hindered by the hydrogens that are also axial. Okay? If we can do the chair flip and twist over to the equatorial version, now we can get that out and away, and it's no longer sterically strained. It's no longer interacting with the hydrogens that are cis to it on that side of the ring. So that's our segment on disubstituted cyclohexanes.